Okay, so I want to tell a story today. I really should have done this on my first class. So I'm going to wind us back a couple months. And we talked about how the conservation of energy arises from something called time translation symmetry, which is that when you have a process that has some result, and then you translate it in time, you do it an hour later or a day later, and you do it the same process again, you get the same result, right? You have a symmetry in your system that has that's due to the fact that you can reproduce physics in time, and that's associated with the conservation of energy. So the story of Emmy Noether is that she's the one who first understood this connection between conservation and a symmetry, right? She's the one who derives the idea that time and energy are correlated with each other, right? Conservation in time means conservation in energy. But she has a particularly sad story, but a good one. In the end, it's been a long journey. So here's Emmy Noether. She's actually a mathematician. I called her a physicist, but you'll understand why I call her a physicist once we hear her story. So she was born in Erlangen, Germany. Her father was a math professor, and she really wanted to be an English person, teach English and German, very much into lit, which at the time was what women usually did when they were academically minded. They tended to be into literature and the arts. But really liked mathematics because her dad liked math. So she really continued pushing to be one of the top math students at Erlangen. And Erlangen is the Erlangen, I forget what it's called, the gymnasium, which is like something in Germany where they have between a high school and a college. Erlangen is a very high prestigious gymnasium, and very good for its physical science and mathematics. But she's only one of two women at Erlangen at the time, right? But she couldn't actually get credit for the classes, right? So she continued to be a teacher of English. Officially, her major was English and German at the gymnasium, if you will, the equivalent of a major. But she only continued to be a mathematics by auditing the classes, right? And the instructor had to give permission, right? So only certain instructors would teach her because she was a woman, and she couldn't get any credit for these courses. And in fact, they almost expelled her because they thought her participating in math was disruptive, right? The quote, literally overthrow all academic order at the university, right? But she graduated, still a great mathematician, and she continued to teach at Erlangen, but did so without pay. She couldn't be a math teacher for pay. But she continued to work on math on the side without pay. Luckily, her parents were middle class and could support her. And then in 1910, her stuff was beginning to be noticed in mathematics journals, and she was discovered by David Hilbert. It's hard to say how famous David Hilbert is. David Hilbert is one of the last great mathematicians. Like if you think of people like Euler and Euclid and the great Descartes, the great mathematicians of the world, Hilbert is one of the last great ones. There are a few others from the 21st century, but 20th century, but Hilbert is truly one of the last. And he invited her to work at the University of Göttingen, which is a very prestigious scientific university in Germany, a very old one. And many physicists, great physicists, worked at this, either taught at this school or went to this school. And so she went to Göttingen. You'll have to forgive me, I can't pronounce the name of that city. One of my closest friends is from there, and I still can't pronounce it. And they said, so when they tried to invite her to come work at the university, originally they said no. The philosophy and the history departments, which were very large at the university outside of science, said no, right? And here's some quotes from the faculty members. What will our soldiers think when they return to university and find they were required to learn at the feet of a woman? Right? After all, we are a university, not a bathhouse. But thankfully, David Hilbert is a very influential mathematician at the time. And at the university, they eventually allowed Emmy to come teach, but didn't have a position, had no pay, no room and board, no research funding, and couldn't teach her own classes. She taught under Hilbert's name. Right? She taught Hilbert's classes for him as a TA. So while she was at Göttingen, she publishes this paper in 1918. Right? It's called Invariant Variation Problems. And it proves this theorem called Noether's theorem. And we'll talk. I think I have a couple of slides. I forgot exactly what's in here, but we talk a little bit about the idea of Noether's theorem. But Noether's theorem, here's a great quote from the Nobel Prize in Physics lecture from '88 from Leon Lederman, who's a great high-energy physicist. The Noether's theorem is certainly one of the most important mathematical theorems ever proved in guiding the development of modern physics, possibly on par with the Pythagorean theorem. Right? So this unpaid, unappreciated female mathematician somehow publishes what turns out to be a very simple idea and changes the course of physics. I'll talk, and I guess I don't have a quote about Noether's theorem, but what Emmy proves is that if you have a system and it has some symmetry in it. So, for instance, the center of mass symmetry, right? If everything moves relative to your center of mass, like a two-body problem, an orbiting problem, a Keplerian planetary problem, or the conservation of momentum, or the conservation of energy. These conserved quantities in physics are associated with a symmetry of the system, right? Conservation of energy comes from this idea of time translation. There's the idea that if you're in a vacuum, that every point in space is exactly the same, and that implies the conservation of mass. And so Emmy proves that this idea of conservation and symmetry are connected, and over the course of the 20th century, physics entirely redevelops itself around this idea. Right? There are many quite such symmetries that people find in physics at different energy scales and different levels of theory. Right? As you go to smaller and smaller particles or higher and higher energy, right? There are certain symmetries that exist and some that are broken. And the result of that is that you lose a conservation, whether conservation of mass or something like that, and you get new physics, right? In some way, one thing is the reason why any particle has mass in the world, the electron, why anything has mass at all is because a certain symmetry of what's called the Higgs field breaks at low energy. Right? This Higgs boson that was detected, right? This is the force carrier for that symmetry, that force, and when its symmetry breaks, that imply at low energy, which is like, normal energies. These are very high energy particles. So a normal world, that symmetry breaks and it breaks the conservation of no mass. And so now everything has a mass. So Noether's impact of physics is again, it's not to say that it's not a hyperbole really to say that it's equivalent to the Pythagorean theorem, right? Trigonometry or Cartesian, right? Coordinate geometry, right? Something like this that has changed the world, or calculus. But anyway, I want to tell you the rest of her story. So after World War I ended, things got better in Germany for women. And so she finally got tenure at Göttingen in 1919. And she finally got a professorship from the government, right? In Germany, the entire educational system is private, or is public, right? Run by the state. So the government gives professorships. And so they gave her this civil servant professorship that was unpaid, but she could teach her own classes, right? So she continued working unpaid until she got her final position in 21. And also did a number of other mathematics studies. She's got some famous things in algebra and topology, which I don't understand at all. And so, but here's the problem, is that when the Nazi Party rose in the 30s, Emmy, of course, is Jewish, and I don't know, so of course, but so many of these stories in Germany, when it comes to famous scientists, they tend to be Jewish. And as I say here, like many prominent Jewish mathematicians and physicists, she had to leave. There's so many stories like this all over Europe. And so she moved to the U.S., and she moved to Bryn Mawr in Pennsylvania, where they gave her actual money. It was her first real paid academic appointment, right? But she only got a 1-year contract. She didn't get tenure. She just got a non-tenure track contract at Bryn Mawr. And she also got a grant through the Rockefeller Foundation because Einstein wrote her a recommendation letter. And then she was later appointed at the Institute of Advanced Study, which is at Princeton. That's where Einstein was at the time, amongst many other famous physicists. And so Einstein personally invited her to come work with him and John von Neumann, Hermann Weyl, just really, tower pinnacles of physics at the time. But she left Princeton. She said no, because this is a men's university. I'm not interested in it. Right? Bryn Mawr at the time was a very liberal school. It still is, and a women's school. So she went back to Bryn Mawr and spent the rest of her life at Bryn Mawr until she died at 53 from sepsis from an exploratory surgery. But she had never had tenure at Bryn Mawr. She just continued for a little while to work there as a non-tenure, and was very famous for she liked to sit with students at lunch, and she was very open, but a very exacting professor as well. But even though she had this kind of life in the background, New York Times published an obituary for her when she died in 1935, and Albert Einstein wrote it. Right? Einstein wrote her New York Times obituary, right? And he writes that Fräulein Noether was the most significant creative mathematical genius thus far produced since the higher education of women began. And of course, Hermann Weyl, who is not a common name, but equally famous for his contributions to not equally famous, but equally important in his contribution to physics. It says Emmy's courage, her frankness, unconcern about her own fate, conciliatory spirit were in midst of all the hatred and meanness, of course, of the 30s, and the sorrow and despair, a moral solace. So it's really interesting. I always like telling the story because we don't, even still today, when we talk about thermodynamics in the chemistry department or any chemistry department, we don't ever look at this story, even though it changes the way we look at physics. And there's really not really a story quite like it. So yeah, that was my Emmy Noether story. Unfortunately, it's completely out of context for the rest of the class right now. But that's I like telling that story. So, any questions about Emmy? Yeah. Okay. So I wanted to continue. That didn't take as long as I thought, which is good. I want to tell another story today, an equilibrium story, about a person much less lovely than Emmy Noether. What we're going to talk about today is what's called the Haber-Bosch process.
Is this stuff
Yeah, this is an equilibrium lecture, so yeah, I would take notes on this one. Yeah, we'll actually do some problems here. All right, and I kind of want to use this problem, and I want to tell a story about the Haber-Bosch process because it's such an interesting story in chemistry. And its namesakes have very different reputations in Germany than Emmy Noether does. So the Haber-Bosch process is very simple. Take some H2, you put some N2 in together. And what you find is that there's an equilibrium to form an H3. And it makes ammonia. So let's balance this real quick. We need 3 of these, 1 of these, and 2 of these. Mix 3 moles of hydrogen, 2 moles of nitrogen, and you're at equilibrium with ammonia, 2 moles of ammonia. And so I want to talk a little bit about the equilibrium about this problem, and it has a good historical significance. But at the turn of the 19th century, or the 20th century, one of the problems that the world was having, right, due to, you can think of the Irish famine and any other famines at the time, is that these are often caused due to poor nitrogen content in the ground. Right? Fertilizer at the time was a rare thing, didn't really exist. Right? And of course, the most major component of fertilizer, right, in order to drive growth, you need nitrogen, right, which is the nitrogen cycle. And so, but there really isn't a good, efficient way of making fertilizer at the time. What they really wanted to make is ammonia. Right? Ammonia is, the problem with nitrogen. Of course, there's plenty of nitrogen out there, right? Our atmosphere is made out of tons of it, but nitrogen is unreactive, right? It's inert. It's not a particularly good reagent to make nitrogen-containing molecules, but ammonia is, right? Ammonia can be liquefied at reasonable temperatures. Right? You can make liquid ammonia at room temperature at low pressure. You can't do that with nitrogen, of course. This has to go to 77 Kelvin. Of course, very hard to do in 1900. Right? But you can liquefy ammonia. It's easy to transport. It's reactive. And you can use it for just about anything. Right? So it's a super useful component. So let's talk a little bit about this equilibrium. We can let's just say, okay, well, let's go make this at home in our garage. We want to make some fertilizer. And so let's just do it at room temperature and do it at 1 bar, right? Room atmosphere. Okay. And we know how to do this, right? We know that to calculate the equilibrium constant, we just need to calculate delta G. Calculate delta G. Well, okay. Well, we know that delta G is delta H minus T delta S. And we know how to calculate enthalpies and entropies. We just go on ATCT, which of course they had in 1900, and look up our enthalpies of formation and our entropies of standard entropies for our materials, right? And calculate the difference. Right? So we can do that. So let me right here, let's do, so what molecules do we need? NH3, H2, and N2. All right, delta H in our table and delta S. Remember, delta S is usually reported in joules, not kilojoules. So we'll have to convert. And delta H is in kilojoules. And we know delta H of F for H2 and N2, there's just 0. They're the natural forms of those two atoms. And ammonia is well documented. It's minus 46.11 kilojoules per mole. So we already know this reaction is exothermic. So the delta H of the reaction is going to be 2 times delta HF of NH3, which is minus 46.11, minus 0 plus 0. Right? H2 and N2 are 0. So this reaction is exothermic by 92 kilojoules per mole. All right, well, that's nice. It releases energy. Let's look at delta S. Again, it's not hard to calculate these things or to look them up. And delta S of NH3 is 192.77 joules per Kelvin per mole. H2 has a slightly smaller one of 130.680 joules per Kelvin per mole. And N2 is 191.609. Okay, so we can calculate delta S for this reaction too, which is 2 times 192. I'm just going to write it shortly, just like this, and then minus 3 times hydrogen. I'm just going to write 131 plus 3 times 192, or sorry, 1 times 192. And this comes out to be negative. Or sorry, yeah, negative. I have that value here. Yeah, it ends up being minus 0.390 kilojoules per mole per Kelvin. Okay, so it's an ordering reaction. It's entropy disfavored, but it is endothermic. And so let's go calculate delta G, which is H minus TS. So that's going to be minus 92.22 minus 298 Kelvin times minus 0.390 kilojoules per mole per Kelvin, which is delta S. But here's the problem. This is minus 92. The negative signs, this is going to turn into a plus. Right, and we have something that's roughly like 0.33, right? A third times 300, that's 100. This whole thing's going to be positive. Right? You counteract that, and so you have a delta G greater than 0, and it turns out to be 23.915 kilojoules per mole. Well, that must mean, so now to calculate K, it's e to the minus delta G over RT. And that ends up being 6.4 times 10 to the minus 3. So that means this is reactant favored. Okay, well, maybe it's not that useful of a reaction. It would be a nice one to do. So H2, it's quite easy to make H2, right? The most common way at the time to make H2 is to take, I think it's methane. You crack methane with steam, and you make H2 and O2. That's the typical way to make H2. And nitrogen, of course, you just extract from the air. This would be a really nice way to make ammonia. But unfortunately, room temperature and pressure, it's not good. Okay. Not only that, we'll come to this when we talk about kinetics after the break. There's also another problem. This reaction is slow. Okay, so to get it to equilibrate, it takes a long time. All right, but we'll have to, let's hold on to that concept and come back to it in a second. Now the question is, how do we change conditions to favor products? All right, how do we make this a product-favored reaction? Okay, so we can't really change anything other than temperature and pressure, right? So let's think about how the equilibrium constant changes with temperature and pressure. So I never derived this in class, but I'll tell you here, this will be really useful, the Gibbs-Helmholtz law. Which says that the derivative of Gibbs divided by temperature, the change in Gibbs with respect to temperature, constant pressure, is just dependent on the enthalpy and temperature. All right, and if you integrate this and assume H is independent of temperature, right, that the heat capacity doesn't play a major role, you can derive that that delta G over T2 minus delta G, so this is delta G at some temperature T2, minus delta G at some reference temperature, divided by the reference temperature, is equal to the enthalpy of the reaction, or whatever process, times 1 over T2 minus 1 over T naught. Instead of T2, I'm just going to call it T. Okay. So now we have an expression where we can calculate the Gibbs energy at any temperature as a function of temperature and enthalpy, right? So what we can do is plug this into this, right? We can plug it into RT ln K, right? And if you do that, it comes out really quickly that the log of the equilibrium constant at some temperature minus the log of the equilibrium constant at your reference temperature is, minus H reaction over R, 1 over T minus 1 over T naught. All right. This is called the Von Toff equation. Right. And this encodes everything we need to know about how the system changes with temperature, the equilibrium changes with temperature. Okay. So all we need to know is the enthalpy of reaction. Assume it's constant over a wide range of temperatures. And look at how the equilibrium constant changes. So let's look at our think about it as our reaction, for our reaction here. So for the HB process, delta H reaction is less than 0. Right, it's exothermic. So let's think about the sign here. So let's assume we look at temperatures that are warmer than our reference temperature, which is room temperature. So this T is greater than this T. Well, the equilibrium is dependent on the difference of the inverses. So if T is greater than T naught, then 1 over T is less than 1 over T naught. Right? Because this is a smaller number than this one. And so this thing's negative overall. Right? So you have a negative number times a negative number, which is positive, times a negative, which is negative. And that implies that K of T is less than K of T star. So as T increases, the equilibrium becomes more reactant favored. Okay, so we can't use heat to drive us. In fact, what this tells us is that we want to cool the system down more, and that'll drive it towards the products. Right? And you can think of that logically in terms of Gibbs. Right? We have a positive sign here. You're adding the entropy to the negative enthalpy. And as T goes down, this contribution becomes less positive. And so you might get a change of sign in delta G. So that's no good, right? We have to go to cryogenic temperatures to get it to go product favored. But here's the problem. The reaction's slow. It's got a big activation barrier. As we'll see, that's dependent on temperature. The colder it is, the slower it's going to go. So as the system becomes more product favored with temperature, it slows down, and it's slower to equilibrate. So you make less over time, right? Engineering, of course, is a balance of the two. It could be all product favored as you want, but if you ain't making products every day, then it's a completely worthless process. Right? So temperature is not going to help us. Right? In fact, we probably want to raise the temperature because we want to speed it up. So maybe we should try pressure. I know my wife knows I'm teaching right now. I don't know why she's messaging me. Sorry.
Did you leave the stove on?
No. She's the one who does that, actually.
Oh.
She'd admit it too, though. Okay, so let's try pressure. Well, here's the problem. K is not dependent on pressure. Sort of. We'll see why I mean sort of in a second. Just T. All right, but we can play around with this a little bit. So let's and I'll show you what I mean by that. So let's write our expression for the equilibrium constant. All right, and we're going to do it in terms of pressures, partial pressures. All right, because we're doing all gases, that's using pressure is a logical way to do a constant volume, a logical way to do concentration. So the equilibrium constant for this reaction is going to be the partial pressure of NH3 divided by our standard pressure, which is 1 bar, just to make it unitless, divided by partial pressure of H2 cubed, over P naught cubed, times the partial pressure of N2 over P naught. We can simplify this a little more by recalling that the partial pressure of some component is its mole fraction times the total pressure of the system. Okay? So let's plug that in. So this is X of the mole fraction of NH3 times the total pressure over the standard pressure, just to cancel units out. Equilibrium constants have to be unitless. You can't take the log of a united number. The log of a unit is meaningless. And we can just evaluate this expression for all of them. So the mole fraction of H2 times P total over P naught to the cube, right? Because there's 3 moles times N2. We can factor some stuff out, right? We got some P totals and some P naughts everywhere, so let's do some algebra. We have 4 powers of P total in the numerator and 2 powers of P total in the, 4 powers of P total in the denominator and 2 powers in the numerator, so the net will be 2 powers in the denominator. Likewise, we have the equivalent P naughts in the denominator, so we'll have 2 powers of P naught in the numerator times the ratio of the mole fractions. Mole fraction NH3 squared, mole fraction H2 cubed, mole fraction N2, like that. Okay. So now what I'm going to do is I'm going to plug that into our expression for delta G. Delta G is equal to minus RT when this thing, xnh3 squared, xh2 cubed, x into P naught over P total squared. So let's think, this is delta G naught, excuse me, at equilibrium. So let's think about changing pressure from this expression. Here's the interesting thing, right? This is RT is fixed. As we know, delta G naught is fixed, right? It's fixed to at the fixed temperature by the difference of the Gibbs energies of formation. This is a fixed number as well. So if pressure changes, so this whole thing is K, right? So if this is fixed, then everything here has to be fixed. The value of K, which is all of this, does not change. However, if we raise the pressure, P total goes up, this goes down, and then consequently, that must mean that the mole fraction ratio has to go up in the equivalent amount. K hasn't changed. But what we've done is we split the pressure part out from the mole fraction part, right? So if pressure goes up, this goes down, and this ratio goes up, which means that the mole fraction of NH3 increases, right? The numerator increases. It's getting larger than the denominator, right? We're making more products, right? So the reaction mixture is dependent on P positively and negatively dependent on T. So when this process was being developed, well, let's look at how pressure changes first. So how K at 400 bar, 200 bar, sorry, 200 bar ends up being the equilibrium constant at 1 bar times 200 squared. And so when you do that, I have the number here. 200 bar. Yeah. Yeah. Sorry. So let me change this again. I apologize. So what we need to do, let me start over. So K is negatively dependent on T. So it becomes less product favored at high T, but at high P it becomes more product favored. But the reaction is slow, so we need to make it fast. So we got to raise the temperature to make it fast. right? So what it turns out, one of the things that these guys, Haber and Bosch, and I'll tell the story in just a minute, is that you have to raise the pressure and raise the temperature to make it fast and to make it product favored. So at 200 bar and 400 C, this ends up being the equilibrium constant at 400 C, at 1 bar and 400 C, times 200 squared. And I should write Kp here. Right? And it turns out that this is, I have the number, 1.64 times 10 to the minus 4 times 200 squared, which is 256. Now it's quite product favored, right? We've made it fast by heating it up because that's the reaction rate increases. And I'll explain why the reaction rate increases in just a second, right? So that we have it going faster at 400 C, and to compensate for the loss of products, we pressurize the 200 bar, and we get a nice product favored reaction. Right, so this is, in fact, this was a huge deal because at the time, the industrial capabilities of making high pressure materials, even at 200 bar, which to today's standards is not massive, it's still pretty high, we're not there yet. Right? You really need high quality steel, very careful systems planning to handle 200 bar, because if that explodes, you're going to kill someone, if not worse. Especially when it's ammonia and hydrogen, you don't want to fuck with that. So let's think about how much NH3 you make with this. So the way we're gonna analyze this is just with a simple ice chart. Okay, and so we'll do ice, NH3, H2, and N2. And let's say we start with our stoichiometric amounts of H2 and N2. Right, so 3 moles of H2, 1 mole of N2, and 0 moles of NH3. Right? And then let's do our extent of reaction analysis. Every time this reaction occurs, we gain 2x moles of NH3, we lose 3x moles of H2, and we lose a mole of N2. So our total change is going to be 2x minus 3 minus 3x, and 1 minus x. So plug that in. 256 is going to be equal to 2x squared over 3 minus 3x cubed times 1 minus x over 1 over 200 bar squared. Okay. Right, we can solve for x. X is 0.98909. Almost complete conversion. Almost complete conversion. Right, you've gone from having 0 moles of NH3 to 2 times 0.98, that's 1.96 moles. How many moles do you lose of here? Well, whatever it is, it's a tiny amount, right? So we have a tiny amount. We almost have complete stoichiometric conversion to NH3. Right? We expect 2 moles out, we get 1.96. That's pretty good yield. Right? All we have to do is pressurize it and heat it up. This class gets out at
45.
Oh man, we have tons of time. Cool. Cool, I got a story to tell about this.
That ice table just gives you serious PTSD.
Oh yeah, me too actually. I hate doing ice tables.
I looked at it, I was like, I have no idea what that does, but I know that I hate it.
Do we understand this approach to doing equilibrium ice? Not really?
That's my favorite approach to do.
Yeah, me too.
Me too.
Okay, so remember we talked about extent of reaction, and we're talking about that the reaction changes by x steps, right? And we track it with x. Right? So the idea is that if we know the initial starting conditions of our system, every time the reaction occurs, how many mole equivalents do we lose? That's the change, right? This is initial change. I don't remember what E stands for. Do you remember, Alex?
Existential dread.
Equilibrium. Existential dread. I like that one. Existential dread. Equilibrium, yeah.
Because that gives you your values at equilibrium. You just
Right.
combine the initial and the change.
Right. So at equilibrium, you're gonna gain 2x of your system, 2x mole equivalents. Here you start with 3, and at equilibrium you lose 3x mole equivalents, right? Because the stoichiometric coefficient in H2 is 3. And here you get 1 minus x, right? And so these x's are balanced so that the equilibrium constant is equal to the value that it should be, 256, right? This number is fixed at T and P, right? So that means that the rest of the equilibrium constant has to be equal to that. And if we start at an initial condition that is in equilibrium, 1, 3, and 0, we can track how far the system reacts, how far the progress of the reaction is, by solving for x. Right? Solving for the equilibrium condition, which is the amount of moles being transferred across the system such that you reach equilibrium. Right? So that you get this side to equal this side. All right, well, I'll make sure to put, so on homework 5, I'll make sure to put some practice for ice charts. Okay, we'll do some equilibrium problems. I've got some good ones. And we'll give you a little practice on these. Okay, and we'll do some more. Because if we don't have that many classes, I might just skip electrochemistry and go straight to kinetics. But anyway, I'll make sure there's some good practice on it. Okay, so this turns out to be a huge deal. And it's hard to say how huge of a deal it is. And I want to read an excerpt from a book about the Haber-Bosch process. The whole first chapter of this book is about, it's actually about the namesakes of these two people. Fritz Haber, he's a chemist. And I'll read a short clip about Fritz Haber and his process. The other one's Carl Bosch. Carl Bosch is the head engineer, or the head, I don't know what you call it now, the CTO of a giant chemical company in Germany called IG Farben, which at the time was a part of the BASF conglomerate. BASF is the largest chemical company in the world, and was at the time and still is to this day. They split off during the rise of the Nazi Party, and Karl Bosch ended up being a giant Nazi. But Fritz Haber's story is very interesting. So the amazing thing about the Haber-Bosch process, this became the first way to make nitrogen commercially. I mean, literally. Right? The only nitrogen that's commercially available is nitrogen gas. And so it was very hard. You can't make amines unless you have ammonia. Right? You can't make any sort of organoamine, any sort of nitrogen-containing compound without ammonia. Right? Ammonia is the true fundamental reactive ammonia species, or nitrogen species. So there's no commercial way to make it. And luckily for us, our atmosphere doesn't have a lot of ammonia like some of the planets in the solar system do. There's not a lot of ammonia here. So this was the first way to commercialize the production of nitrogen. And this revolutionized the world. So I want to read this. But what I want to talk about in particular is Fritz Haber. Fritz Haber, in some ways, as we'll see, in this excerpt, is the savior of the world. Remember, we're at the verge of a multinational food crisis at this point, because most of the world had been stripped bare of any usefulness by the Europeans over centuries and centuries. And so, as the world industrialized, they realized there wasn't any agriculture, right? Because the world's Africa and East Asia and stuff had been basically stripped bare and left for nothing. And there wasn't a way to efficiently make nitrogen for their soil without this process. Okay, so I just wanted to read an excerpt from this book. And so what it says here is what Haber achieved in the laboratory, Karl Bosch, chief engineer at the German chemical giant BASF, refined into an industrial process capable of producing hundreds of tons of nitrogen in a factory the size of a small city, operated by more than 50,000 workers. The Haber-Bosch process is the most important chemical discovery of the 20th century. By doubling the amount of disposable nitrogen, it provoked the demographic explosion that took the human population from 1.6 to 7 billion in fewer than 100 years. Today, nearly 50% of the nitrogen atoms in our body are artificially created, and more than half the world population depends on foodstuffs fertilized thanks to Haber's invention. The modern world could not exist without the quote, "the man who pulled bread from air," in the words of the press of the day. Though the immediate aim of his miraculous discovery was not to feed the hungry masses, but to provide Germany with the raw material required to continue manufacturing gunpowder and explosives during the First World War, once the English fleet had blocked access to Chilean nitrate. So you'll see throughout history, the South American mineral trade is very important. So Chile at one point was the West's only source of nitrate outside of the Chinese, who were not all that interested in sharing it with anyone but the British, and that was mostly by force. And nowadays it's Venezuela. Venezuela is the home of the largest exporter of lithium, which you need for batteries. So the next one will be Venezuela, which is of course why Venezuela has so much foreign influence in it in order to make sure the lithium continues to flow. Anyway, I digress. Haber's nitrogen allowed the European conflict to drag on for 2 more years, raising the casualties on each side by several million. One of those who suffered from the prolongation of the war. Let me skip that. I don't want to care about that. I wanted to continue about Haber. Emboldened by his successes with nitrogen, Haber proposed to reconstitute the Weimar Republic and pay war reparations that were strangling its economy through a process as wondrous as the one that had won him the Nobel Prize, which was harvesting gold from the waves of the sea. Traveling under a false identity to avoid raising suspicions, he gathered 5,000 samples of water from assorted seas across the globe, including bits of ice from the North Pole and Antarctica. He was convinced he could mine the gold dissolved in the oceans, but after years of labor, had to accept his original calculations that overestimated the quantities of this precious metal by several orders of magnitude. So after that failed, he found research in his work as director of the Kaiser Wilhelm Institute for Physical Chemistry and Electrochemistry as anti-Semitism continued to flourish around him. Fritz Haber was a Jew, as was Karl Bosch. Protected for the moment in his academic oasis, Haber and his team produced a number of new substances. One of them was used cyanide in a pesticidal fumigant so destructive that it was dubbed Zyklon, the German word for cyclone. The compound's extraordinary effectiveness stunned the entomologists who used it for the first time to delouse a ship covering the Hamburg-New York route. They wrote directly to Haber to praise the, quote, extreme elegance of the eradication process. This new success led to Haber's promotion to National Commissioner for Pest Control, from which post he organized the extermination of bed bugs and fleas on the Navy submarines and of rats and cockroaches in the barracks. He fought against an invariable legion of moths that attacked the flour the government stored in a network of silos that stretched from Flensburg to Freiburg, which Haber described his superiors as a, quote, biblical plague that threatened the well-being of the German Lebensraum, unaware that they had already begun the persecution of all those who had shared his Jewish roots. Haber converted to Christianity at 25 years old. He identified so closely with his country and his customs that his sons knew nothing of their ancestry until he told them that they would have to flee Germany. Haber escaped after them and sought asylum in English, but his British colleagues scorned him, aware of his instrumental role in chemical warfare. He had to leave the island not long after arriving. Thenceforth he would travel country to country in hope of reaching Palestine, his chest gripped with pain, his arteries incapable of delivering sufficient blood to his heart. He died in Basel in 1934, which is Switzerland, clutching the canister of nitroglycerin he needed to dilate his coronary vessels, not knowing that years later the Nazis would use in their gas chambers the exact pesticide he helped to create in order to murder his half-sister, his brother-in-law, his nephews, and countless other Jews who died hunkered down, muscles cramping, skin covered in red and green spots, bleeding from their ears, spitting foam from their mouths, the young one crushing the children and the elderly as they attempted to scale the heap of naked bodies and breathe a few more minutes and a few more seconds because Zyklon B tended to pool on the floor after being dropped through the hatches of the roof. And among the few possessions Fritz Haber had with him when he died was a letter written to his wife. In it, he confessed that he felt an unbearable guilt, not for the part he had played, directly or indirectly, in the death of untold human beings, but because his method of extracting nitrogen from the air had so altered the natural equilibrium of the planet that he feared that the world's future belonged not to mankind but to plants, and that all was needed was a drop in population to pre-modern levels for just a decade to allow them to grow without limit. Taking advantage of excess nutrients humanity had bestowed upon them to spread across the earth and cover it completely, suffocating all forms of life beneath a terrible verdure. So I really like telling this story because Fritz Haber, in some ways, is the ultimate dichotomy in science. In some ways, he saved billions of lives and then also killed millions as well. Because I didn't tell the story, but all of the gases, many of the gases that were used during World War I during trench warfare, were invented by Fritz Haber and processed to BASF through his process, through his many processes. So Haber, in some ways, is one of the most controversial chemists in the world because of the vast difference in negativity and positivity of his contributions to the world, in some way that you can't match with anybody else, I think. And it's amazing how simple this realization is, right? The idea is that at equilibrium, right, all you can do is change a couple of things. You got temperature, you got pressure when you deal with gases. Right? And temperature was, right, and what he realized is that not only to speed up this reaction, he also realized a really amazing thing, which is that when you design the system, you can drive the system towards process even further. So what he does is he feeds H2 and N2 into his system. I guess this is really Haber-Bosch's invention, but we'll claim them both. And what he feeds them into is this honeycomb filter at high pressure. So this is at 400 C, this is at 200 bar, this is at 400 C, and there's this honeycomb filter. And inside of this honeycomb, I'll just kind of draw it like this. Inside of this is a mixture of, I think, iron, and I think it's potassium permanganate, but I could be wrong about that. It's either a peroxide or a permanganate, suspended in this high temperature ceramic honeycomb, and this acts as a catalyst, right? Because what happens is that you have this metal surface, this iron metal surface, and your H2 comes in and attaches to the surface like this. The HH bond breaks, and you form two metal hydrogen bonds, two metal hydride bonds. Right? And so then it turns out that the nitrogen then can come in and attack, right, consecutively. Right? Eventually it just starts to break these bonds. It just picks the hydrogens up. This is not real mechanism, but the idea is that it sequentially picks these hydrogens up and then equivalently kicks the nitrogen out. We'll talk about the mechanism of it later. Right? And this is much faster than these just two colliding. Right? That doesn't work. That's extremely slow. But if you break the hydrogen first, the nitrogen will come in and just pick that hydrogen atom right up. And in order for this to work, for hydrogen to be able to leave the metal surface, right, with the desorption, as we call it, the scientific term for that is desorption, you need high temps. Right, so you have to turn the system up to 400 Celsius to get the catalyst to start going. Right, and that speeds up the reaction dramatically. And what he does is very simple. He feeds this mixture out. Right, this mixture is H2 plus some N2, and of course there's some ammonia in here. And he ammonia has a lower boiling point, has a higher boiling point than hydrogen or nitrogen. So you cool this down to, say, I don't know, T equals 200 Kelvin, like that. And you can collect the nitrogen in a pool, or the ammonia in a pool. Right? And so what you do is you feed your hotter gas that doesn't condense back into here, so you have mostly hydrogen and nitrogen and just a tiny little bit of ammonia that doesn't condense back into the system. Right? And you can drive this process in continuum, right? You can continue to do this, right? The cool thing about this is that you have an equilibrium mixture of H2, N2, and NH3 here. And since you have more reactants than products in equilibrium, we'll say that this system will continue to react and make more ammonia. Right? So you get this nice feedback loop. The gas, the H2 and the N2 can feed through here as you feed in fresh, of course, right? So you have a recycling of the remaining hydrogen and nitrogen left over after the first reaction. And then you just drive the reaction forward a little more by removing the NH3 out of the system and liquefying it. Right? And this can just get on a truck and go wherever. Right? You can just put them in, you can just put your dewars in here. Right? And so this ended up being a huge deal. Right? This revolutionized everything when it came to agriculture. Right? Any sort of nitrogen production. Right? This is the entire basis. In some ways, this is the entire basis, or one of the most important of modern chemical engineering. This concept of large-scale nitrogen content, nitrogen production. And of course, this process of using a honeycomb, what we call a heterogeneous catalyst, it's heterogeneous because it's a different phase than the materials, the reactants. Right, we use this in your car every day, right? This honeycomb pattern that has of high temperature ceramics coated in metals is what forms a catalytic converter, right? If you cut a catalytic converter in half, this is what you see. You see a honeycomb with some platinum and palladium coatings, which processes the unreacted fuel that doesn't get combusted in your car. Right, same process. Any questions about that? Okay, guys, that's about all I have today. So again, class is canceled on Tuesday. Are you holding CLR hours on Monday?
On Monday I'm not, but on Tuesday, if you're canceling class, are you guys gonna bother doing homework on Tuesday? Because I can do Zoom hours since most of you will be leaving Tuesday, or I can just cancel my hours altogether. So it's up to you guys. I can do them on Zoom. I don't think any of you guys are really going to be here Tuesday.
I was going to hold something on Monday.
Okay.
Will anyone actually come to anything on Monday? Any interest in that? All right, maybe I won't then.
Enjoy your break.
All right.
When's the homework due again?
Next Friday, before we get back.
Okay.
Yeah. Yeah,
Are
so
you gonna
next.
finish the homework tonight? Probably not.
How deep are you into it? The hardest problem on that is 2 and 3.
Yeah. 2 I keep messing up explaining. I need Sean's help on that one.
5 looks complicated, but it's really not, if you just think about it.
Your key doesn't have 5
I know it
on
doesn't.
it.
Did you figure out 5?
I think I got the gist of it. I just wanted to run it by
I will send you something about it.
Okay.
Yeah, have a lovely break, everybody. We'll be back. We'll start. I'll have to decide, is anyone actually interested in electrochemistry, or would you just rather go straight to kinetics?
Oh, we can go straight to
You want to do
I
electrochem?
would be interested in electrochem.
All right.
I am, but if you don't want to do it, you don't have to.
Sorry, you prevented majors.
Yeah, let's do electrochem. All right, we'll do electrochem when we get back. One lecture of electrochem, because it relates to equilibrium,
So you guys don't have batteries for it?
and then we'll do kinetics.
Hi.
Hi.
I was just wondering if you saw my email
I did.
before. Okay.
I did.
I'm sorry.
That's okay. Don't worry about it. No worries.
Have a good break, but you're going to see half of us tomorrow.
Let's get out of
Oh yeah, that's right. I'll see some of you tomorrow. That's right.
Thank
I
you.
forgot about that.
See you tomorrow, Dr.
Yeah, see you tomorrow.